All right, so in your packet. Page 2. At the very bottom, we finished that problem, but I want to kind of let's see. I want to talk about the advantages of using log properties before our derivative process. So on bottom page 2, this is what we worked through before you guys took the test. We went over this on Friday. So we talked about how for number 7 here, anytime we see a natural log expression where the u value feels complicated, we can always use log expansion to make our problem easier and simpler to work with. So natural log of a over b, I can expand into natural log of a minus natural log of b. And then we got all the exponents to show up and bring down in front. And we only want to expand to the point where we feel like our u value for our derivative is easy, right? Or easier, right? Relatively easy. X squared is a relatively easy derivative. 2x cubed is a relatively easy derivative. So then we do 2x over x squared. For the second term, the 1/2 stays, but then the u prime over u is 6x squared over 2x cubed. We simplify, but no need to find common denominator. Okay. So that's where we left off for 5.1. Now, let's go to page 3. And let's talk about this process called log differentiation. So page 3, log differentiation. The idea with log differentiation is that we want to basically introduce logs into the problem. Introduce logs into the problem so that we can take advantage of log properties. Okay. We only want to do log differentiation if there is no logs to begin with, and we want to introduce logs into the problem. So if I look at this problem here, y over x minus 2 squared over x squared plus 1, with the square root. How would you normally, what would you involve here if this was given to you and you're just using rules that you knew? If I should find the derivative. Quotient rule and chain. It's doable, right? But it's a little long, right? We're going to have to go through 2 sets of chain rule within quotient rule. And now we have an alternative to basically break that problem down into easier parts. So if we can introduce logs into the problem, then all of a sudden we have logs available to us. So I'm going to take the natural log of both sides. Okay, so whatever we do to one side, as long as we do to the other, we're still maintaining balance. I'm going to rewrite that square root here. Now, if we look at that right side, now that my right side is a log expression, what property can I use to break that into easier parts? What does that look like to you? Natural log of a over b, right? Which property can I use for that? Quotient property, right? Natural log of a over b can be expanded into what? Yeah, natural log of a minus natural log of b. So now we have basically smaller problems to solve. Okay, so we haven't done anything with derivatives yet. Okay, all we're doing is we are doing all these steps so that our derivative can feel easier. Okay. Okay, what else can we do to expand? exponents can what? Go in the front, right? Both sets of exponents. So now all my expressions feel relatively easier or much easier than before. So now I'm just going to take the time to find the derivative of each of these three terms. Okay. But something is different on the left side here. Y is no longer by itself. Now there's something, y is underneath natural log. So guess what we have to do when we find the derivative? Anytime y is stuck in something else, we got to do what? Remember that process? Or if I asked you for this problem here, remember this from chapter 2? Yeah, we got to do implicit, right? So implicit differentiation because y is stuck inside this natural log expression. Okay. So natural log of y becomes, remember the derivative rule for natural log is u prime over u. So natural log of y becomes 1 over y. And then we need to include times dy dx. Okay. Moving on to the right side here, 2 natural log of x minus 2. The 2 will stay. And then what's u prime over u for my expression here? Yeah, 1 over x minus 2. The 1/2 stays, that's just the coefficient. And what's my u prime over u for my second term? Yep, 2x over x squared. All right, so we found the derivative. Now we just have to kind of rearrange things to clean things up a bit. I'm going to skip example 4, so we're just going to carry our work down to the example 4. We'll do example 4 later on a separate sheet. Okay. Okay, so our goal is to get what by itself? We found the derivative, so what's our derivative variable? dy dx, yeah, we're just trying to get that dy dx by itself. Or think of the dy dx as your f prime, right, or your y prime. We're just trying to get that derivative by itself. So what needs to move? Yeah, that y. So when that y moves over to the right side, it's going to end up where? Numerator, right? Because if I multiply by the reciprocal, it's going to end up in the numerator. So our dy dx equals y times, right? I'm just multiplying by the reciprocal, moving that y over to the right side. I'm going to just clean up each of these fractions, but I'm not going to have to do any common denominators. I do see a reducing step that I can take. The 1/2 and the 2 can clear out. I can take away the 2. I'm just left with minus x over x squared plus 1. Okay, we're almost done. We have our derivative. But notice that we started out with a completely normal function, right? The x's and y's were not mixed. So that means that we should be able to represent our derivative purely in terms of x as well. We shouldn't need y in our answer. But y is kind of like a temporary variable to kind of get us through this process. And now I want to replace y in terms of x. Can I do that? What's y equal to? The original, yeah. So I can just replace my original expression in for the y, and that, makes it messy, but at least we're able to represent our derivative purely in terms of just one variable, right? It's a function, so we shouldn't need the y to get involved in our derivative. So when we do log differentiation, it's just going to feel a little messier because the idea is that we're taking something that is compact, we're breaking it into smaller chunks, and then we're taking the derivative of each of the smaller chunks. So our derivative may look a little different than if we were to go through this using quotient and chain rule. But the advantage is that we're able to expand using log properties so that our derivative feels a little bit easier. Rather than having to deal with one large problem, we can break them into smaller parts, easier parts. Okay, so we have two scenarios where we want to use log differentiation. The first scenario is where it's a convenience purpose, where we would prefer not to go through quotient and chain rule and product rule, and we're relying on this alternative method because we have that option. Okay. There's a second type of problem where we're forced to have to go through log differentiation because we have no other way to handle it. So I want you to look at this. Look at example 2 here. Look at the way that this is set up. This is a variable raised to a variable. Okay. And I want to kind of talk about the fact that we don't have a rule that can handle a variable raised to a variable. Okay. This we don't have. Okay, but what we do have is something like this. I want to just kind of talk about each of the different types so that you can kind of see it. What if I have a variable raised to a constant? What rule can I handle with a variable raised to a constant? So this would be what? X squared, right? This we can use what to find the derivative? Just power rule, right? Variable to a constant, we're good with, we can handle that. What if I have a constant raised to a variable? So for instance, this would be like 2 to the x. This is an exponential function. Okay. We have something that can handle exponentials, and we'll get to that in the next section. Okay. So variable raised to a constant is x squared. We do power rule for that. A constant raised to a variable, we have exponentials. We can handle that, but we don't have something that can handle a variable raised to a variable. Okay. So whenever you have variable to a variable, we have to basically find a way to get it in a different form. Otherwise, we can't handle it. So the idea is that what if we take the log of both sides, which will then allow that exponent variable to move to a different location, which will then open up opportunities for us to try different things. So we start off with y is equal to x to the 2x plus 3. So if you see a variable raised to a variable, you're going to have to go through log differentiation, okay? Because we don't have a rule for this, and log differentiation allows this problem to be presented in a different form. So now that we have both sides under a natural log umbrella, what can we do? What property can we apply to get that right side to look a little differently? Okay. Power property, right? Power property. So we'll bring that 2x plus 3 down in front. Okay, times natural log of x. Okay, so now, like before, I can do the derivative the same way as before. Left side is 1 over y dy dx. And what can we handle on the right side here? Okay, now that exponent is down in front, we have a derivative rule that can handle this setup. What do you think we can use to find the derivative of that right side? You have two expressions. What's the operation between these two parentheses? Multiplication, right? So we can use product rule because, right, product rule, we can handle this. We couldn't handle this form, but we can handle this form. Okay, so we're going to apply product rule here. This is product, not product property. This is product rule for derivatives here. Okay, f prime g plus f g prime. Okay, so natural log of y becomes 1 over y dy dx. Okay, f prime g plus fg prime. Okay, what's f prime going to be? Just 2 times the g function plus f g prime. G prime is what's natural log of x turn into? What's u prime over u? 1 over x. All right, so we have our derivative, basically. We just have to move the y to the right side, get that dy dx by itself, and replace the y back in terms of the original variable. So again, I'm going to use the space below. Okay, and then replace the y back in terms of the original variable. Okay, so we see there's 2 different types of problems that log differentiation can be used. One is where we prefer not to go through a messy combination of chain, quotient, and product rule. And the other is where we're forced to have to go through log differentiation because in the current form, we just don't have anything that can handle a variable raised to a variable. But if I can bring that variable down in front, then all of a sudden I have some availabilities for me to apply these derivative rules. I have some options available to me. Now, on the AP exam, if you're going to see a log differentiation problem, a lot of times it's going to be in this category, okay, where they want to see, can a student recognize the need for log differentiation, and then to apply it, and then to go through product rule and implicit to get to the end. So if you're going to see log differentiation, it's going to usually fall into that second category. Okay, let's go to the next page. This is 5.3. Let's talk about inverse functions. Okay, so let's review inverse functions. Inverse functions are where x's and y's are swapped. And because x's and y's are swapped, your domains and range are also swapped. Graphs are symmetric over the line y equals x. So for instance, if I have y equals x squared and x equals y squared, these are inverse functions, right? If I replace the x in terms of y, right, and the graphs will look a little differently. Right, so maybe you got y equals x squared here, x equals y squared will look like this. But essentially, visually, you can kind of imagine yourself kind of folding across the diagonal line, and the 2 graphs will match up with each other. Okay, they will kind of fold over each other. Okay, if you were to fold it across that dotted diagonal line, y equals x. And the unique thing that we're going to really discover, or that we're going to really use, is the fact that your order pairs will be flip-flopped, right? So if there's an order pair here that is 2, 4, then guess what order pair is going to live on the x equals y squared? Not 2, 4, but what? 4, 2. Okay, so that is a property that we're really going to kind of be able to understand with, or be able to kind of start to have as a starting point, is that your function and your inverse will always have flip-flop order pairs, and I call these corresponding points. Okay, so there's an order pair here, 3, 9. There's gonna be order pair here, 9, 3. Okay, so on and so forth. So if a function are inverses with each other, I can plug one into the other, and I'm able to reduce everything down to just an x. Okay, so here's a quick example before we talk about the derivative side of things. It says find the inverse of the function y equals 6x plus 2. So the inverse, I'm going to first swap the x and y. That's the first step. In the second step, you're going to solve for y. So if I swap x and y, I get x equals 6y plus 2. If I want to solve for my new y, I'm going to subtract 2 from both sides. Divide both sides by 6. And that is my inverse function. And the way I write my inverse function, I'm going to change that y to a different variable. I'm going to call it f inverse of x. We're going to skip example 5. And I want to use this space to kind of introduce the topic of derivative of inverse at a point. But I think it's easier if I can introduce it to you, giving you a picture rather than giving you something that is abstract. Okay, so here's what I want to draw for us here. So using that space, I'm just a different sheet of paper so I can have more room here. I'm going to have us draw this here. So let's say we had a graph. And let's say we want to put both the function and its inverse onto the same graph. Okay, so I'm going to have us draw this graph here. There's a dividing line. Let's call this the original function. And a different color, I'm going to draw in the inverse. Okay. You can kind of imagine, I know this is not to scale here, but kind of imagine how this visually could be a function in its inverse, because if I can fold the graph over the across that diagonal line, I can kind of imagine that these two graphs are going to kind of overlap each other. Okay, so that's what function and its inverse is always going to do. You can always fold the graph, and the two graphs will always overlap each other. So let's say there's an order pair on this graph that is 1, 4. So if there's an order pair of 1, 4 on the function, then on the inverse, there must be an order pair of what? 4, 1, right? Because that is, if a function and its inverse, if we can call it its inverse, they're always going to have that flip-flop property, okay? And I call those corresponding points. Okay. Okay. So I know that f of 1 is equal to 4. I know that f inverse of 4 is equal to 1. Okay. So that is on the function side of things. Okay. Now, there's also a specific relationship in terms of their slope. Okay. And I think it's nice to see from a visual perspective. What does this slope look like over here? Positive and pretty steep, right? So let's just say f prime of 1, let's say the slope is 7. Okay. So f prime of 1 is equal to 7. Now, over here, this slope over here has a numerical connection to this number here. So the f inverse, the derivative of f inverse of 4, right? Obviously not the same point. It's a different location, so it's different x value. What do you think the slope of this is, knowing that there is a connection with this number? Good, 1/7. Okay, you knew it wasn't negative 1/7 because they're both positive slopes, but it's a lot more gradual. So that's really the lesson for today. Okay, at their corresponding points between the function and its inverse, their slopes of their tangent lines will always be reciprocals of each other. Okay, so we're going to be kind of discovering this relationship here. You need? Yeah. All right. So I want to kind of establish some this chart that I use to kind of help me move through this process, and then we can kind of use this in our problem today. Okay, so I like to create this chart here. Okay. Up here, I'm always going to put the order pair relationship between the function and its inverse. Okay, so for instance, over here, we'll just use this example for now. Okay, f of 1 is equal to 4, and f inverse of 4 is equal to 1. Okay, and then I'm going to put the derivative relationship down here. The derivative of f inverse of 4 is equal to 1/7. The derivative of f prime of 1 is equal to 7. Okay. Now, the way that the problem is going to be given to you is going to be like this. Okay, the problem is going to give you what they're looking for. Okay, so you're going to start off on this side of your diagram. And you're trying to figure out what is the slope of the f graph of the inverse function at 4. Okay. But the problem is that you're not going to be given the inverse function. Everything that you're going to be given is going to be in terms of the function. So what we can do, though, from this alone, we can kind of fill in our chart across, in the circle here. So I know that I know 4 is the x value of my inverse. And if 4 is the x value of my inverse, then 4 must be the what? Y value of my original function. Okay, so you're going to start off with this as your beginning, right? You're going to be given this x value and can fill this chart up to this point. And now you're going to be given the function, which you can kind of work algebraically to figure out what the x value is. And once you get that x value, let's say it was 1. Algebraically, we'll figure out that it's 1. And if our x value is 1 here, then we know the y value of 1 is there. And because everything is going to be given to you on the function side of things, you can work with that function, find the derivative, okay, evaluate the derivative at that x value, and then you're going to get that number 7. Okay, let's just say, for instance. Okay, and then once you have this, then you can turn around and you can make your conclusion without ever touching your inverse function, because everything that you have is on the function side. So this is 7. Again, this must be 7. Okay. It's always going to be the same sign slope. It's just reciprocals of each other. So if this is negative 2/3, then this must be what? Negative 3/2, right? So you're going to keep the same sign. You're just going to flip your numeric value. Okay. So using this table here and this diagram and this concept, we're going to attempt example 6. Okay, so let me walk you through example 6 here. Okay, so we're going to find the derivative of f inverse at -3. Okay, so I know that if I want to go through, I like using my chart here. It kind of helps me organize my information. I know ultimately I'm going to end up here, but I'm going to be working my way around this diagram. Okay, so I'm looking for the derivative of f inverse at -3. Now I know my -3. I know -3 is the x value of my inverse. So my first column, first row, I'm just going to put down information on the order pair side of things. Okay, I don't know what the y value of my inverse function is, but I do know that -3 is the what of my function, the y value. Now everything that I have is on the function side of things, so I'm kind of forced to use that function. So is there a way that I can solve for x if I know what the y value is? Plug in -3 in for what? In for f of x, right? That's the y value. So I can kind of work backwards here to figure out what that x value is. Okay, so I'll say -3 equals. I'm going to add 3 to both sides here just to see if this will be easier to solve. Okay. Now look at, we want to find the x value that fulfills this order pair here. Is this factorable? Okay, I'm not able to factor. Okay, and you're going to see this in the textbook as well, where you can't factor it, but it's going to be a relatively easy number to find. You're going to have to kind of do a little bit of guess and check here. But the numbers will be easy to find. Okay, it'll be numbers close to 0. So you only need to really test values between like -3 and 3. Okay, and after you cycle through a couple of numbers, you should be able to find that relatively easily. So let's just go through some numbers here to see, okay, what are some numbers that could work for x that will make this a true statement? Yeah, because if I think about positive numbers, nothing's going to work, right? All these positive numbers will just get larger. Even 0 is not going to work. But if we try -1, -1 cubed is -1, -4 is -5, -5 plus 5 is 0. So we know that my order pair of -1, -3 is going to work, right? I plugged in the y. I couldn't factor. I'm guessing and checking my way through, but I saw that my x value is -1. Okay. So if -1 is the x value of my original function, then -1 must also be the y value of my inverse. So we see that flip-flop order pair relationship between the function and its inverse, right? Just like what we would expect with the function and its inverse. But now, if I can find f prime of -1, if I can find the slope on the f side of things, then that slope is going to, that numeric value is going to lead me directly to where I want to, what the slope of the inverse at -3. So before I can find f prime of -1, I can first find what? F prime. Right? I have f of x, I can find f prime. So f prime is relatively easy. What's f prime going to be? 3x squared plus 4. I can now evaluate the derivative at -1. And what do I get? Okay, kind of a coincidence here. So if the slope on my f graph is 7, then the slope of my inverse that I'm looking for must be what? 7. Okay, so I like to use this chart to kind of help me organize my information. I know ultimately I'm gonna end up here, so I'm gonna go around, gather information. By the time I make my way full circle, I have enough information to reach what I'm looking for. Okay, so let's try example 7. Okay, not every problem is going to be a guess and check. It's just that some problems ends up being that way. You're going to see that in your textbook as well. Okay, y equals square root of x cubed minus 7. We want to find the derivative of f inverse at 1. Okay. I know this is my end goal. I know 1 is the x value of my inverse, so I can just go ahead and put that order pair information in, but I don't know the full order pair. So again, if 1 is the x value of my inverse, then 1 is the what? The y value of my original function. And now what can I do with my original function to find? I can find my what? I can find my x, right? So what would you do from here?
Plug in y.
Yeah, plug in 1 in for y, and let's work backwards and solve for x, right? Okay, so I think this one we can do algebraically. We're not going to have to do a guess and check. I can square both sides. Add 7 to both sides. And I can take the cube root, right? What's cube root of 8? 2, right? So I can fill in some of this information that was missing. I know I've order pair 2, 1 that lives on my function, which means on my inverse, there must be an order pair 1, 2. And if I know my x value of my function, I can move towards finding f prime of 2. And whatever I get out of that, then I know numerically I can come to the conclusion what the slope of the f inverse is at 1 without looking at the graph, without touching the inverse function at all. We're just doing everything on the function side. So before I can find f prime of 2, I first need to find what? The derivative, right? And the derivative here, if I rewrite it using rational exponents, what do I have to involve here to find the derivative? Not product. Power and chain, yeah. This is outside, inside, right? Outside is that parentheses of the 1/2. Inside is that x cubed minus 7. Okay, so let's find the derivative, y prime. Outside's derivative, go through power rule. 1/2 parentheses to negative 1/2 times the inside's derivative, x cubed minus 7 becomes 3x squared. Do some cleanup here. Bring the square root back down to my denominator. All right, so now I have y prime. What can I do with that y prime? plug in what? Plug in 2, right? Now I can find y prime, y is the same thing as f. So plug in 2 in for my y prime. And 3 times 4 is 12. Cube root 2 cubed is 8. 8 minus 7 is 1. Square root of 1 is just 1. 12 over 2 is just what? 6. So if f prime of 2 is 6, then the derivative of f inverse of 1 must be what? 1/6. Okay. It's not the same thing as perpendicular lines, right? We don't do opposite negative reciprocal. Okay? You just do the reciprocal. Okay, don't change the sign. Okay. Any questions? Okay, example 8 and 9 are easier because if we just go through our chart, we can just fill in whatever is missing and then arrive at our answer without having to do much math. Okay, so let's look at 8 and 9. So example 8, this g of f of x equals x indicates that g and f are inverses of each other. We have some information given, and then we have our goal. Our goal is to find f prime of 2. Okay, so I'm going to use my chart here. I'm looking for f prime of 2. I know that 2 is the x value of my function or of my f function. So if 2 is the x value of my f of x, then 2 must be the what? Y value of my g of x, right? I don't know what my x value is, but just from the very beginning, I can fill my chart in up to this point. And now we want to look at what's given to us and see what we can fill the blanks in with. Do I have something that I can fill in here? G of what is equal to 2? Yeah, I have that information, right? So g of 7 equals 2. I can go ahead and fill that in. So if I have order pair 7, 2 here, my function will have order pair 2, 7. So if I can find g prime of 7, the slope of my g graph at 7 is going to numerically correspond to the slope of my f graph at 2. Do I have information about g prime of 7? Okay. So if the slope of my g graph at 7 is 10, then the slope of my f graph at 2 must be what? 110. Okay, spend a minute to do example 9. It should go fast. Same process. Okay. I know 3 is the x value of my f of x. So I know 3 must be the y value of my g. What can I fill in this space here? G of 9, right? That's given to me. G of 9 equals 3. So I have order pair 3, 9. Now, sometimes you may be given some extraneous information here. So sometimes they may give you information that try to throw you off. They'll say maybe g of 3 is equal to 6, but we don't use that, right? We only use what is going to match with what we've already built. So if I can find g prime of 9, then g prime of 9 will lead me to my answer. What's g prime of 9? Negative 4. So f prime of 3 must be what? Yeah, keep the sign, just take the reciprocal. All right, so you guys have some homework from 5.3. I'll check 5.1 and 5.3 tomorrow. Okay, all right, come to get your phones.